VBE arm, which is 0.7 volts, plus beta plus 1 times IB times RE, which would be 100 kiloohms times IB equals 0. Because remember, we have beta plus 1, or this is IE equals beta plus 1 IB. So that point, we can solve for that and say 2.3 divided by 2, 87.5. And we'll get that IB equals 8 microamps, which means that IC, this is Q, sorry, this is the DC value, so ICQ is going to equal 0.792 milliamps. And this is enough for me to know that this actually is in the forward active region, so we can keep going forward. From there, we need a couple of small signal parameters. We have transconductance. There's going to be ICQ over VT, 0.792 divided by 0.026. VT is that constant related to Boltzmann's constant temperature and the charge of an electron. Which is going to equal 30.46 milliamps per volt. Our output resistance, RO, we're going to say lambda is infinite. Write that on there. Lambda is 0, not infinite, which is going to be infinite. That means. Then our pi equivalent, that diffusion resistance, R pi, is going to equal beta VT over ICQ, which is going to equal 99 times 0.026 over 0.792 milliamps volts. It's going to equal 3.25 kiloohms. There actually is a fourth small signal parameter that we can use, and it's going to be helpful to us. And that's what fourth parameter is beta, which is equal to GM times R pi. This is going to be the current gain as opposed to the current relative to the transconductance. Is just the current gain. And so this is GM. So the IC equals GM VBE. VBE equals IB R pi. IC equals beta IB. We can also just say this, and this is just going to equal beta, the value we had over here. It's very helpful to us. It's just 99. You can plug that back in, you'll see that's the case. Because ICQ cancels out, VT cancels out, just get beta. And we're going to use that this time as opposed to the transconductance. So transconductance is useful for us to solve sometimes, but as we'll see when we go to solve this circuit, it's going to be a lot more helpful to have everything in terms of beta IB than GM VBE. So again, build the AC equivalent circuit. We short out DC sources. That becomes voltage sources. That becomes a short to the ground. That becomes a short to the capacitor. Short to the capacitor. And then remember, we have a path from base to emitter via the R pi equivalent resistor. And then we have path from collector to emitter. That's that controlled current source. In this case, we're going to call that beta IB. The IB is just the current to the base. From there, I can just finish building the rest of that circuit real fast. This is RC, RE, R1, R2, and then RS, and
Excuse me, Professor.
yes, VS.
On the DC analysis, when you got the VVV and then you got the try to find the IVQ, why you
Yes.
like 100 kilo ohms over there and multiply by
Yes. Because this full equation is actually negative VBB
uh-huh.
plus IB RB, where RB is just those two in parallel,
Yeah.
plus VBE ARN
Uh-huh.
plus IE times RE.
And the R is 1 kilo ohm, right?
RE is 1 kilo ohm, yes, but IE
Mhm.
is equal to beta plus 1 times IB. And so to get rid of that extra unknown, I replaced IE with this equation right here. So it becomes 99 plus 1 times 1 kilo ohm. So it becomes 100 kilo ohms.
Oh, okay. Thank you.
Yep. It's a good question. That's going to come up a lot during the exam. So not a lot, but it'll come up during the exam. So make sure you catch that. That's good. So that's our AC equivalent circuit. It'd be nasty to solve this in this form. Let me solve V out over here, actually. We don't really want to solve this in this form. We also have a path to ground here and a path to ground over here. This is an ugly circuit. We don't want to solve this. So instead, I'm going to simplify it. I'm going to do that on the next slide, probably just so we have space to work. Is everyone okay if I move on?
Yes.
Okay.
Yeah.
So just real fast and write this down. R pi equals 3.25 kilo ohms. Okay, and beta equals 99. Then I said 300. R1 in parallel with R2 equals 187.5. Okay. And then this is 2 kilo ohms, this is 1 kilo ohm. Okay, so now simplify the circuit down. We have a path from V out to ground through VCC, so I'm actually going to work backwards this time. You can work in either direction. So you have a path through V out to ground right here through RC. And you also have a path from V out to ground through the emitter junction. Which is that controlled current source, through RE all the way to ground. This is not done because from the emitter right here, we have a path also out to the base, draw right here, through R pi. And then we have a path from base to ground through R1 in parallel with R2, either this way or this way. And then we have a path from base to ground through RS in series with VS. And so we're going to define a couple things that are going to help us more than anything else. Because this is an ugly circuit right now. I'm going to draw two lines right here. I'm going to call this RIB. This is the input resistance to the base itself. So if you're actually looking at the circuit, this is what the resistance the current experience moving into the base of the circuit. This right here is RI. This is the input resistance into the overall amplifier. So this region right here is our designed amplifier. We're trying to design. So RI is the input resistance experienced by the circuit going into the amplifier as a whole. RIB is the input resistance of the circuit going just into the base of the BJT. Basically, it's ignoring R1 in parallel with R2 and just looking at this resistance. That's going to save us a lot of space in terms of writing our equations out, because it's really ugly if we don't. And it's also going to help us simplify a thought process of how this actually is working. So from there, we're just going to do a couple things. We're going to first of all say, okay, we know V out, but we don't quite we do. We actually know V out. That's fine. So V out right here. This is IB moving into here. Beta IB moving into here. Through here we have IE, but that's a path to ground. So right here we're only moving through IC. So the current through RC is just IC, which is equal to beta IB. So V out is equal to negative beta IB because of how we're measuring the voltage relative to the current flow, measuring the opposite direction, times RC. Some people try and take this extra IB and apply it through RC. There's no way for IB to get over there because it's going to take a path to ground as opposed to going back through RC. So the only thing you'd look at is this part of the current right here. So it's just negative beta IB times RC. Unfortunately, we got to find a way to derive IB. And deriving IB is a lot easier than figuring out the voltage drop across just this R pi resistor, because you have to find IB in order to solve for that, essentially. Which is why we're not doing that. And so we can write a couple of things. We can say, well, the voltage at node B right here is equal to the voltage drop across R pi, so IB R pi, plus the voltage drop across RE, so IE RE. We also know that IE, or it should be a little e, I apologize, because we're in the AC equivalent. And also know that IE is equal to beta plus 1 times IB. Because this is beta IB, this is IB. It's going to be the same rule as before. And so we can say that VB equals IB R pi plus beta plus 1 IB RE. And from that, we can actually figure out RIB, because RIB is just going to equal VB over IB. So we can just pull IB out of that equation. And our resistance into the base of the circuit itself is just R pi plus beta plus 1 times RE. Any questions on that? It's kind of a weird thought process to some people. Make sure I'm actually doing this example problem correctly from here, because I don't want to do it blindly and tell you wrong. No, it's right. That's fine. Yep. Okay. So from there, we have to define something else. We still don't have any way of writing this entire circuit. However, we can see one other thing, in that Ri, our input resistance, is just equal to R1 in parallel with R2 in parallel with that RIB. And we can also write an equation saying that VB itself is equal to Vs times Ri over Rs plus Ri. That still hasn't given us quite enough to go on, because we still don't have an equation for IB in relative to Vs, right? So from there, and I'm going to move over to the left side of it, which I don't like to do, but I want to keep all the equations on the same page. We're going to say that, okay, we know that VB is equal to this. We also know that VB over IB is just equal to VB over RIB. And now we actually have an equation we can plug back in. Because we can plug in, this is equal to VS times RI over RS plus RI times 1 over RIB is equal to IB. And so now we can go back to our initial equation for V out. Now you can just say, and I'll go back to that last slide. Actually, I was stupid here. And we can just say that V out is equal to negative beta times RC over RIB, which is R pi, plus beta plus 1 times RE times RI over RS plus RI times VS. And if you want to make that AV instead of V out, so the voltage gain itself, we can just divide both, make AV equals V out over VS. We can just say this.
What did you just do, Professor?
Oh, I wrote this in terms of voltage gain, AV, which is equal to V out over VS. So I took the equation for V out and divided it by VS to get AV. So it's going to equal V out over VS.
Okay, thank you.
Yeah. And so in a well-designed circuit, well-designed is a very, very flexible term, and the idea that R pi is much less than beta plus 1 times RE. That's not quite true in this case. 3.25 is not much less than technically 100 kilo ohms. It's less than, but it's not significantly less than. And also in the case where RS is much less than RI, which again in this case actually could be true, because this will push up the stability of this region right here, because RIB is a much larger value than R pi. And this is 300 ohms, so this could actually be true. But essentially what you'll see is that AV can be approximated in this case as just negative RC over RE. So you can get a rough approximation of what our gain should be. This would be the upper limit of our gain, actually, by taking negative RC over RE, in this case, negative 2 volts per volt. In practice, for our circuit, again, I'm going to go ahead and go to the next slide, if that's okay. I'll rewrite all this stuff right here real fast. AV equals V out over VS, negative beta RC over R pi plus 1 RE times RI over RS plus RI. And we make the assumption that RS much less than RI, R pi is much less than beta plus 1 RE, and I guess technically 1 is much less than beta. We can get our upper limit of AV is approximately equal to negative RC over RE, which for our cases would be 2 volts per volt. In practice, we can plug our values in and say that negative 99 times 2 kilo ohms divided by 3.25 plus 100 times 1 kilo ohm times, and we haven't done that yet, so 187.5 in parallel with 3.25 plus 100. which is $66.58 kiloohms over 0.3 plus 66.58 kiloohms. That one is actually a pretty good approximation of 1. It's 0.9956 times 198 divided by 103.25. AV negative, sorry. Which gives us an AV equals 1.91 volts, negative. So you can see it's not a perfect approximation, but it'll give you a really good initial guess for any of your problems like this, which is really, really helpful on a large test problem, especially when you have multiple choice questions like this. If you're trying to rush to the exam, you know RC, you know RE, you can eliminate some answers if they exceed negative RC over RE, right? This should be negative, sorry. So if I give you a test question, what is the voltage gain of the circuit, and I give you RC is 5 and RE is 2, and 3 of your answer choices are greater than 2.5, you've gotten rid of all but 2 answer choices there. So it's a really good way to speed yourself along on some of these problems. And it's also a really good way to check your answer, because you should have closely approximated, or you should see why it doesn't closely approximate it. The reasons it wouldn't do so is I gave you a large value for RS that would really drag this down. Or I made it where R pi is relatively large compared to this, which is harder to do. It means I had to use a small beta. So for smaller values of beta, it's not as good of approximation. For, again, large source resistor inputs, it's not a good approximation, but otherwise it's a very good approximation. So this is ideal. This is actual. It's a really good approximation. It'll save you a lot of time on those kind of problems. Are there any questions on this?
Excuse me, Professor.
Yes.
Do you mind? Can you explain the AC circuit one more time? How you build that?
Yeah, I'm actually going to work on a problem just like this, so
okay.
I can happily do that. I like to. This one's a harder circuit to grasp. I like to go through it twice. Once with the talking through the whole theory, and once it's actually just solving a problem. And it's kind of the same process, but I think it's helpful to just to show you how I solve a problem like this. So I'm gonna go ahead and just make a new circuit real fast. We'll say VCC is 10 volts. R1 is 600 kiloohms. R2 is 400 kiloohms. Make my life really easy. RE we're gonna make 500 ohms. RC is going to be 3 kiloohms. Beta will equal 87 amps per amp. VBE ARN equals 0.7. Lambda equals 0 inverse volts. And then we'll make this 5 kiloohms just to get a more annoying example. And so I want to know input resistance to base, input resistance to amplifier, and I want to know voltage gain. And we solve all these as we go through the problem anyway. So first thing I have to do again is DC. VB is going to equal 4 volts. IB is going to equal 3.3 volts divided by 4 plus 1 over 6. 240 kilo ohms plus 44 kilo ohms which will equal 11.6 microamps, which means IC will equal 1.01 milliamps. That puts us in forward active because 10 minus basically 3 minus 0.5 is still greater than whatever the saturation limit would be. So 2, the
Dr. Matson, was VB
Yes.
already given, or did you pull that from the
I
circuit?
solved that. So yeah, VB is going to be the Thevenin equivalent circuit here. It's
Okay.
equal to VCC times R2 over R1 plus R2. And
Gotcha.
RB is equal to R1 in parallel with R2. I'm skipping steps because we went through DC analysis in a lot of detail, and I can
Okay.
I can just look at DC and do it quickly. You shouldn't do it that way. I'm giving you a bad practice on that, so thank you for asking. It's helpful to build your DC equivalent circuit and solve the Thevenin equivalent. There's nothing tricky about this problem, so I'm just skipping a step. But yes, always make sure you solve it because I can make mistakes too. So yeah, VB is this, RB is this. That's where I got the 240 from. And again, that loop, this is beta plus 1 times RE. Okay, and then so small signal parameters. I'm not going to actually use transconductance. I'm going to solve it anyway just to get practice doing it. It's not hard to do anyway. It's just ICQ, which is 1.01 milliamps, over VT, which is 0.026 volts, which will equal 38.84 or 85 technically milliamps per volt. Again, I'm not going to use that. I'm going to use beta is 87. R pi is going to be beta VT over ICQ, which will equal 2.24 kilo ohms. And RO is going to be infinite. Whenever we have this emitter resistor down here, I will always make lambda be 0 for any practical problem we're going to solve, just because if not, it's a hodgepodge mess of mesh analysis on top of the circuit analysis. So step 3, we're going to simplify our circuit and replace it with its AC equivalent. Again, this. And then step 4, we replace the emitter, the BJT, with its AC equivalent as well. And again, I give myself space to do that. It's really hard to see where I'm drawing with this. It doesn't show up well to me. There it is. Okay. And so then this gives a path from base to emitter through R pi, and then a path from collector to emitter through beta IB. So step 3, AC equivalent circuit, basically superposition rules. Step 4 is AC transistor. Next, we want to simplify. And I'll go through how I did this in a little more detail. You can either work from V out or you can work from VS. Pick one of the two. It doesn't matter which one you work from. I did V out last time. I'm going to work from VS this time. So I'll go VS is right here. And my first spot where I have to make any decisions is this node right here. So I go through RS to get there. And I have a spot at this node right here. And I'll call this node V sub B. It can be confusing to call it that if you don't want to. You can call it V in. You can call it whatever you want to call it. Just make sure you call it something that makes sense to you. At that node, we have a couple paths to ground. We can go through R1 to ground or R2 to ground. So I'm going to call that R1 in parallel with R2 because there's just two parallel resistors. Alternatively, I can take a longer path to ground, where I go through this R-pi diffusion resistor and then down through the emitter resistor to ground. And so, I put that in the wrong spot. Not an artist, I don't have good spatial awareness. So I can go through R-pi, and then down to the emitter, and then through RE to ground. From here, I go back and start working from V out instead and try and connect the two circuits. So over here, I have V out, and I have a path to ground through RC. So, and I have a path to ground through beta IB and then that emitter resistor, which means I get to connect the two circuits just by doing collector beta IB to the emitter resistor. And now my circuits are connected, and this is the circuit I want to solve. From looking at this, I can draw this right here. Again, RC is in series with beta IB, which means they're going to have the same current. And so we can say that V out is equal to negative beta IB times RC, which is nice for our purposes just because, again, we don't have to do anything all that special to get there. This is also very nice for us simply because we don't have to, this is nice for us because we don't have to worry about this junction right here when we solve this because of how the circuit's designed. Anything that IB contributes will go to ground before it comes back around over here. From here, we have to begin to solve the rest of the question that it asks us to solve. We want the input resistance to the base, which we call RIB. We also want the input resistance, RI. We'll start with RIB because it's the next step of the circuit anyway. So again, I call this node VB. You can call this node whatever you want to call it. Just remember that voltage sources in parallel are the same. So we have a voltage source drop from R1 in parallel with R2 to ground. And we also have a voltage drop from VB to here to ground, which will be the same amount. And so we can see that VB is equal to the current through this, which is IB, times R pi. And we can also say it's plus the current through right here, which is IE, times RE. And then we can also remember that from looking at this, we have IB moving into here, beta IB moving into here. IE is beta plus 1 IB. And so I can see that VB equals IB times R pi plus beta plus 1 RE. And to define that resistance right there, RIB, it's just Ohm's law. So RIB equals VB over IB, which is equal to R pi plus beta plus 1 RE. And we can go ahead and solve for that real fast. That's 44 plus 2.24. So RIB is equal to 46.24 kilo ohms. The next thing we want to solve is that input resistance to the amplifier, so the overall input resistance is experience. So that's just going to be R1 in parallel with R2 in parallel with RIB. Because any current moving into here is either going to move through R1 in parallel with R2, or it's going to move through this path through RIB. So that's going to just equal, we did this a minute ago, 240 kilo ohms is R1 in parallel with R2 in parallel with 46.24. So RIB is going to be or RI, our input resistance, is equal to 38.77 kilo ohms. I have to go to the next slide to finish solving the circuit, or I can erase stuff on the left. I'm going to erase stuff on the left if everyone's okay with that, just so I can finish solving all on one slide. Okay, so now we can say VB equals VS times RI over RS plus RI. And we can also say that IB equals VB over RIB, which means that IB equals VS over RIB times R in over RS plus RN. And we can plug this value for IB back into this V out equation. We can say that our V out is equal to negative beta times RC over R pi plus beta plus 1 RE times RI over RS plus RI. Our ideal voltage gain that we talked about before would be just 3 over 0.5, which would be 7. So ideally, our voltage gain is 7. Oh, this times VS, sorry. So AV is just going to be divided by this. So AV is going to equal negative 87 times 3 over, we just said RIB is 46.24 times 38.77 divided by, and I made RS large this time just so we have that issue, 5 plus 38.77. I just divided both sides by VS to get rid of VS. Which gives me an AV equals negative 5 volts per volt. So it's less than 7, but it's not as close to 7 as it was before because beta is smaller. RIB is also smaller. It's closer in value to R pi. So R pi had a bigger role in our loss here. Beta being smaller also brings it down a little bit even more. In addition, RS being 5 drags us down a whole lot more. And so AV is this, which should be our voltage gain. Those are the 3 things you really want to solve for in this circuit. I could also ask you for the small signal parameters. One important thing to note, because every year I see someone do this, is we get these values from this DC analysis. We do not use them except for to find the small signal parameters. All the DC analysis does is determine the small signal parameters of our circuit. It does not play a role at all in the analysis of our circuit. Once you have the small signal parameters, never go back to those values. Without fail, someone will always try and go back to those values. Again, you can also solve this by trying to use transconductance in VBE, but you have to solve for IB on the path to doing that. That's why I don't like to do that. Are there any additional questions, concerns? Good time to end the class. Actually, lasted the right amount of time today. I'm excited about that. Again, I posted all those practice problems, videos, and quizzes if you look at and do. Went over that at the start of the class. The due dates for those, we can go back to in just a second. But I need to quickly get who's in the classroom today.
Okay, 26.
Head out. Don't forget these upcoming dates. I posted quiz 5 and quiz 6 this morning. One's due a week from today. Other one's due a week from Friday. So MOSFETs and BJTs. There's lots of videos kind of going through the same stuff we went through today for all these different topics, talking through the theory behind them. There's practice problems specific to different circuit design types. And then exam 2 is 2 weeks from today, which means we have a little bit of time, but we're finishing up this new material fairly soon. Friday, we're going to introduce a couple other circuit types for BJTs, and then next week we're going to go through a bunch of different circuit types for both BJTs and MOSFETs in practice. And then Monday, the 19th, will be review day, and then 21st will be an exam. It's going to be a similar format to last time, and I'll post your exam 1 grades. They're done. I just haven't gotten them updated. I'll post your updated exam 1 grades probably tomorrow, so you have those. But exam 2 is 2 weeks away. So any other concerns, questions, anything like that?
Is anything from exam 1 going to be on exam 2?
Other than the basic theory of semiconductor devices, no, because I mean, specifically, yes, because for BJTs, you're doing diodes. There's a diode from the base of the emitter, essentially.
Mm-hmm.
Those kind of topics, yes, but specific to, diode-related questions, no. Each exam is going to be focusing on the topics at hand just because we have enough that we're covering. The final exam is cumulative and can replace your lowest test grade, and it will have everything.
Okay.
But, yeah. Okay, y'all have a great day, and I will see you on Friday.
You too.
VBE arm, which is 0.7 volts, plus VBE arm, which is 0.7 volts, VBE arm, which is 0.7 volts, plus beta plus VBE arm, which is 0.7 volts, VBE arm, which is 0.7 volts,